Hello, everyone. I'm Dr. Chem, and welcome to this explainer. Today, we're going to demystify one of the absolute most powerful analytical instruments in modern science, inductively coupled plasma mass spectrometry, or ICP-MS. But, instead of just looking at a bunch of abstract diagrams, we're going to take a journey. We're going to shrink ourselves down and follow the epic, chaotic, and totally fascinating lifespan of a single sample droplet as it travels from a standard laboratory vial straight through a blazing argon fire and into a high-vacuum sorting chamber. By the end of this university-level explainer, you'll know exactly how we uncover trace elements all the way down to the parts per trillion level. Okay, let's dive right into this. We're going to trace our sample's journey through 6 critical stages: the origins of analytical plasma, sample prep and nebulization, plunging into the argon fire, the vacuum interface, filtering by mass, and finally analyzing the data. Section 1. Origins of analytical plasma. Early plasma sources. Before we really get into the modern machinery, we have to understand the core phenomenon, plasma itself. This is a term officially coined by Irving Langmuir back in 1928 to describe structures that were first explained by J.J. Thomson. Now, early concepts from the 1960s and 70s, things like direct current arc deformations, plasma jets, and the Kranz burner, these were absolutely crucial stepping stones. What's really interesting is how they essentially paved the way for spectroscopists like Greenfield and Boumans to harness the high-temperature induction plasmas we rely on today, literally changing traced elemental analysis forever. Section 2. Sample prep and nebulization. Preparing the liquid. Let's step into the present-day lab. Our sample usually starts its journey in liquid form. Maybe it's environmental water or a digested biological sample. But to actually be analyzed, it needs to get airborne. So here's the sequential pathway our liquid droplet is about to take. It's aspirated from its vial, nebulized into a fine mist, atomized into individual atoms by extreme heat, and finally ionized. And by ionized, I mean it will literally have electrons ripped away to form a charged ion. It all starts at the sample introduction system. A peristaltic pump uses this constant motion on polymer tubing to draw the liquid up and push it straight into the nebulizer. Inside, a stream of argon gas acts like a really violent wind, instantly converting our liquid droplet into a fine aerosol spray. That mist then enters a glass spray chamber, which basically acts as a filter. It allows only the absolute finest droplets to pass through, while the larger, heavier droplets just hit the walls and go down the drain. So now our finely tuned aerosol is perfectly ready for the torch. Section 3. Into the argon fire, the ICP torch. This is where things get really intense. Our fine aerosol is leaving the gentle environment of the spray chamber and heading straight for the awe-inspiring core of the machine. The ICP torch consists of 3 concentric quartz glass tubes, and wrapped right around the end of this structure is a heavy copper induction coil, which is powered by a radio frequency or RF generator. When alternating current flows through this coil, it creates an incredibly powerful oscillating magnetic field. At the same time, we continuously flow argon gas through these quartz tubes. To ignite the plasma, we use a Tesla unit to discharge a single spark right into the gas. This spark instantly ionizes some of the argon, creating free electrons and cations that accelerate back and forth inside that intense magnetic field. The resulting collisions generate a stable plasma fire that burns continuously at roughly 6,000 degrees Celsius. When our sample aerosol enters this extreme environment, it is instantly dried to a solid, vaporized into a gas, atomized, and finally ionized into positively charged cations. Section 4. The vacuum interface. Bridging the gap. So our sample droplet has now been completely obliterated, right? Leaving behind just a stream of elemental ions. But here is the critical engineering challenge of ICP-MS. We have incredibly hot plasma at atmospheric pressure, but our delicate mass spectrometer operates in a high vacuum at room temperature. How do we possibly bridge them? Well, the crucial point is this 2-step depressurizing chamber. The plasma gas first hits a water-cooled metal plate called the sampler cone, which has a tiny hole right in the center. The gas rapidly expands and cools as it enters the first vacuum stage. A fraction of that gas is then passed through a second, much sharper cone called the Skimmer cone, entering the main high vacuum chamber. This clever step-down design extracts the ions safely. But we still have a problem. Out of 1 million ions generated in the plasma, only 1 actually reaches the detector. We absolutely have to separate our target analyte ions from a massive cloud of uncharged neutral species and blinding photons, which otherwise just cause a ton of background noise. To do this, we use the ion focusing region. A series of metallic plates and cylinders apply electrostatic voltages to literally steer the charged ions of interest off-axis and safely into the mass spectrometer, while the uncharged photons and neutrals just crash harmlessly into a physical barrier.
Section 5, Filtering by Mass. The quadruple filtrum. Our ions are now safely inside the vacuum and focused into a tight beam. It's time to introduce the core analytical engine of this instrument. Meet the quadrupole. Think of it as a highly selective sorting hat, or maybe a strict nightclub bouncer. It receives a continuous stream of different elemental ions, but it only allows very specific elements to pass through to the detector at any given microsecond, based entirely on their mass-to-charge ratio.
And this brilliantly illustrates how it works. The quadrupole operates using 4 parallel metallic cylinders. We apply rapidly alternating direct current and radio frequency voltages to these rods. As ions travel down the center path, they begin to spiral. By precisely tuning these electrical fields, only an ion with a specific mass will have a stable trajectory and make it to the end. All the other ions spin out of control and collide with the rods. We can literally scan across the entire periodic table in mere milliseconds. To really appreciate this mass filtering approach, it's helpful to briefly contrast it with an older cousin, ICP optical emission spectroscopy, or OES. OES relies on light, often using a shell optics. Now, a shell uses physical cross-disperser prisms to separate light into a two-dimensional bell-shaped spectrum. But a shell optical systems suffer from order hopping, where resolution degrades at the edges of wavelengths, causing stray light and background noise. By physically counting mass instead of sorting light, ICP-MS avoids these optical aberrations entirely, granting us vastly superior sensitivity.
Section 6, Analyzing the final data, the quantification step. We've successfully sorted our ions, and now they strike a detector, generating a tiny electrical pulse. How do we actually turn that into useful science? By measuring the magnitude of the ion current, we can determine exactly how much of an element was in our original sample. We do this by creating a linear calibration curve, plotting known concentrations against the counts per second, or CPS, recorded by the instrument. A statistical least squares regression is applied, and the goodness of fit, our R-squared value, tells us the reliability and precision of our measurement. We also look at the relative standard deviation, or RSD, to ensure our measurements are totally reproducible. Now, to calculate the instrument detection limit, or IDL, we rely heavily on the standard deviation of the background noise. To find the absolutely smallest detectable amount, we multiply the background noise standard deviation by 3 and divide that by the net analyte intensity. Alongside the detection limit, we also evaluate the background equivalent concentration, or BEC. Unlike the IDL, which focuses on the statistical noise, the BEC expresses the raw intensity of the background signal itself as a Mach concentration value. It essentially tells us how much apparent concentration is just inherent baseline static in the machine. Let's tie that math together visually. If 1 part per billion of an analyte produces a towering signal peak of 10,000 counts per second, you can clearly see how it stands out from a low, rippling background of just 1,000 counts. Because the standard deviation of that background noise is incredibly tight, say just 32 counts, our actual detection limit drops to a staggering 0.011 parts per billion. This tight background control is exactly how ICP-MS achieves such incredibly low detection limits. What an epic journey our sample just took. We started with a simple liquid droplet, used a nebulizer to convert it into an aerosol, and plunged it straight into a 6,000-degree argon plasma. We navigated the vacuum interface, used electrostatic lenses to focus a beam of ions, and utilized a quadrupole to sequentially filter those elements by their precise mass-to-charge ratio. Finally, we turned those ion counts into incredibly precise, ultra-trace quantitative data on a computer screen. You now understand the profound physics and engineering working seamlessly inside an ICP-MS. With the power to separate and quantify the very building blocks of matter at parts per trillion levels, what hidden trace elemental secrets will you uncover next in your lab? Keep questioning, keep analyzing, and I'll catch you in the next explainer.